Okay.
Okay. Hello. We are Jimmy, Paul, and Gerald from ICS 4A, and we're going to show you our load balancing projects that we've been doing throughout the semester. So, the load balancer is a customizable load balancer, and the idea behind it is that whenever uh, requests are made from uh, clients, they can be forwarded to any server replica that is available at that particular time, depending on their health condition. So if a server is healthy, they are viable to receive the responses. However, we'll see that any server replica can be able to receive the the request, and they'll reply to the client. So to start off, we'll start with task one. So task one was about uh, creating a minimum of three server replicas. As you can see, at the initial starting of the load balancing project, we have three server instances, and at first, before we added the consistent hashing, there was a bit of uneven load balancing because the first server was getting a lot of was handling majority of the load, so it wasn't doing it. And then we will see from the analysis that will be done by Paul how we manage to do the load balancing effectively. So at the start, I created the main the main server file, and the main server file essentially has two routes. We have the home slash home route, as you can see at the bottom of the terminal. Uh, this route uh, is able to give a response to the client, showcasing its ID as well as whether that whether it was successful or not. So this is uh, a get response, and it's supposed to show the identity of the server, that's the replica that is replying to the client. And then another important thing that we added was the heartbeat, which will be it's a health check endpoint that right now, as you can see at the bottom, it returns a success message, HTTP 200, because uh, we are seeing that it is monitoring the availability of the server replicas. Right now, if you were to check the replicas that are available at that particular time and which are healthy, you can see there are the six of them, and they're all healthy. That is why heartbeat was showing a success message. So I'm going now to talk about task three. Task three was majority. The bit was talking about how the majority of the load balancing was being done. So I implemented it in this particular file, app.py. So app.py is it does three things. First of all, it is like an API. It showcases the main uh, management for the API, which they show whatever the main management APIs of a particular app, such as the get uh, for the client, the server replies, the replica replies, and then the heartbeat health check, as we had seen. And I'm going to take you through how exactly that works. So to begin, we see that it first instantiates the Flask app as it was in the server app, and also instantiates the consistent hash mapping, which is supposed to route all the server replicas according to the hash mapping tool that has been done by Gerald. And we will see how that is being done. So we'll be using a memory control plane that has a memory that stores the name of the container as well as their server IDs. And as you can see from this particular function is showcases how the Dockerized containers are being run by shell commands dynamically by Docker, especially when because it's a load balancing project. So it's all being done in the backend. The constant hash mapping uh, pool function. So at first, uh, whenever there's an addition or a removal of a particular server, it is passed to a pass scale payload function. This one is a validator function that checks whether that JSON is is good or not, which it's valid or not, that is. And if it's not, it will return an error because it's not there. And also make sure that the naming is okay and that it has no empty string. Yeah. So these particular functions are for naming the servers, and whenever a server is spawned or created, you see that it is first registered. That is, it is the at the background the Dockerized container that is started for that particular server. So it is registered and then it is added to the consistent hash mapping ring pool. So it will be part of the rest of the servers that are there. So once all that is done, we'll see that we also see that there's another function, the removal function. So if you want to remove a particular server, for example, I had removed uh, a server. So you can either kill a particular server or not. So the good thing about our load balancing project, if you are to use the normal Docker kill functions, it will still work. You will see that working. So, for example, the earlier killed this server F9UX8, and when it was killed, it took less than 0.3 seconds to create another server, and that was done dynamically without the client seeing whether a problem was had occurred. So you can either kill through either the removal function, as we will see from the APIs that we have, or just a normal Docker kill, which will remove it dynamically from the list. And then this we also have a heartbeat monitor. The heartbeat monitor is the one which is supposed to replace dead replicas automatically, as I had shown you. Whenever you kill a server, that server is automatically removed from the consistent hash mapping, and you can no longer see it. And yeah, it is removed completely. So this we also have another API route called the replicas route. It's supposed to get the number of the replicas as I had shown you from here. You see the number of the replicas here and their IDs which have been created as we had seen in the function for creating. So it creates using a uh, random choices of the ASCII digits. And then once that is done, um, this is now the route for adding. It's a post. It's a post that add particular server. So if you want to add a server, you add them using this particular route, and it automatically adds it to the hash mapping tool. And then the removal also removes them, removes the requested replicas, and even if you are to write the first few digits, because it will supposed to, and unless you haven't written enough digits that can differentiate it from another one, it will automatically add the rest of the digits and then remove that particular one. Yeah, so that is it, it is good because you don't have to write all the entire name of the server replica that you want to remove. And then this route is a dynamic route which happens in the background. So it's like for example, as I've shown you using this home, uh, the home function, the home route that is being directed from the main server file. This one, whenever a client wants requests for something, there's, there are many replicas or otherwise known as boxes. So this particular route, uh, it routes the traffic to any particular server replica that is available at particular time, and they are able to reply to the client. So if any of the endpoints that's like for example, if I was to write Ava, you'll see that it will give an error because that particular endpoint does not exist. So this function also dynamically routes all the available routes that are being used in our system. So if it is if if that route exists, as you can see, either using another different route, home, heartbeat, or rep, it will always be a successful message. And then now this is the main where the entire load balancing actually starts. We first start by spawning the initial three servers for the startup. So this the Dockerized containers, they are all running, and we can see that they are running from localhost at 45,000. So Gerald will take us through the consistent hashing. Gerald,
Yeah, I'm going to be sorry about that. I'm going to be talking about how we implemented the consistent hash, and I'm just going to start with I'm just going to talk about it a bit first. First of all, consistent hash is just it's primarily used to solve the problems that were there with earlier versions of hashing, like the traditional hashing, which was used when scaling web servers or distributed caches up or down. In standard like load balancers or caching systems with, let's say, X servers, you would distribute traffic using a simple modulo hash, which is basically the key divided by the module n, modulo n, which is n being the number of servers, right? This would work okay, but it wouldn't deal with edge cases like what happens when you add a server or when a server fails, because it means the formula would all existing key hashes would all the existing keys would hash to a completely different server than before if you're adding, and if it failed, the formula would change for every key. So consistent hashing solves this by placing both the servers and requests onto the same circular ring of slots. A request is routed to whichever server slot comes next, going clockwise from the request's own position. This way, only this way, adding or removing a server only reshuffles a small fraction of requests instead of all of them, which is whatever happened for all which traditional hashing. So can you go to the consistent hashing? I'm going to so scroll up, no, the first function. So this first default H, given you gave us some quadratic functions we are supposed to implement, and the first one is for request mapping. It's I squared plus 2I plus 17, and then it's modulo m, right? Uh, Actually, before that, I'm going to, in the init constructor on line 21, this is where we define all our parameters, right? Which is the total number of slots, which defaults to 512, and the virtual servers per container, which defaults to 9 because we're using log2 to 12 to 512, which is 9. So back to our quadratic functions. The first function, it maps a client request to a ring, and then which is I squared plus 2I plus 17. And then the second function, it maps a physical server into its virtual replica, J, which is also added onto the ring. Can you scroll? Yeah, and then on line 34, this is where now whatever you told us we were told to implement mostly. This probe function, it's supposed to help with the collision resolution, right? Because multiple server replicas might like might hash to the exact same slot on the 512 ring. This code implements linear probing using the probe helper method. If a slot is already occupied, it steps clockwise, one by one, like sequentially, until it finds its first free index. And then we have the ring operations, basically the add server, remove server, and get server. It now provides the API required to orchestrate the load balancer, as that was shown by Jimmy. The add server replicates a server container k times for each replica j, and it also computes the hash slot using the five function that we passed up earlier, and it resolves collisions with the probe. After it does all this, it registers the physical server ID onto the slot. After that, remove server, it clears out all virtual slots associated with the targeted physical server ID, setting them back to none. And then get server, it basically maps an incoming client request ID to a particular ring index, to any specific ring index. It then moves like clockwise to find the nearest empty slot, basically. Then not the nearest empty, the nearest occupied slot, and returns the response and returns the resulting server ID. In this particular code of ours, I'm going to talk about a weird edge case we run into. Theoretically, now that because we've implemented it like this, it's if for example in our dummy code we were demonstrating this with we have a function called smoke testing here. We are demonstrating it with like 3 servers. Theoretically, it should be bringing like 33%, 33%, 33%. In our code, because of the hash functions we were given, they were, I think, not robust, or they were not like enough that it would result in a high skewness. Like, for example, in our first server, I think we got 85%. Then the second one was 4.5%. Then the third one was 10.4%. I don't think it's there, but this was just when you are still running it. However, this doesn't really affect it because these servers obviously don't handle only three servers at a time. I think it's because we had 3 servers. Server ID squared, you get like, let's say the server ID was 123, server ID squared was 149. And because server ID is supposed to separate one server's virtual nodes from another, it would result in like a large range, even though the number is small. Uh, yeah, basically, I think the easiest way to fix this would be using like more more tested hashes like MD5 or SHA, because I feel they wouldn't like they wouldn't they're robust enough to avoid such mistakes. Or or we would make the server term scale with the ring size. This is even easier because it's a quick fix and it keeps the quadratic form of the original functions you gave us. I'll now move on. Paul will now take you through the rest.
Okay, so I'm going to take okay, I'm going to demonstrate the analysis that we did. We'll start with this bar chart, the one bar chart, which was generated from the test load file, which had 10,000 requests sent to the load balancer while the 3 servers were up. And in that we see that there's an uneven distribution. Server 1 handles way too much requests, and while the other servers have low distribution. So next we look at the consistent hash file. So there we have we found out that the original hash function spread the virtual servers across the 89 out of 512 slots on the hash ring, and the large empty region caused many requests to wrap around the same server, creating an imbalance. In the test scaling file, when we ran, we generated the A2 file, the A2 chart. When we run test scaling, yeah, right. So here we can see the script repeats the test with 2 to 6 replicas, but while sending still the 10,000 requests each time. So the chart tells what happens in that file. As we added more replicas, one server still handled a lot of the traffic, which confirmed that the issue was the hashing strategy that was there. Oh, sorry. Okay, on the the app file, we saw that the endpoints rep, add, rem, and home all worked correctly. So we simulated a server failure by killing one of the running containers. When we killed, the heartbeat mechanism detected that failure and removed the failed replica and launched a replacement. So the entire recovery took about 3.3 seconds, showing that the full recovery worked as expected. So on the test load file and the test scaling file, so these two scripts have the same experiment, but with the alternative hash functions implemented on them. So on the A4 load distribution generated by these files, the A4 load distribution chart, here we see an improvement. The new hash function that we have used managed to spread the virtual servers across 503 out of the 512 slots compared to the 89 slots that were there before. So this is we can say it's a fair distribution. Here we can see the traffic was shared across 39%, 33%, and 28% across the 3 live servers. And a full line chart, also generated by the 2 files, shows the same improvement. From 2 replicas to now 6 replicas, and we see there's no server that's dominating the traffic. The load remained much more balanced at every scale. So during all the tests that we have done, we recorded 15 failed requests out of the 10,000 at 4 replicas, and 23 out of the 10,000 at 6 replicas. So the improved implementation was kept in a separate experimental branch. And as I finish up, we completed all the 4 tasks. We built Dockerized server replicas. We implemented consistent hashing. We also developed a dynamic load balancer with automatic scaling and failure recovery, and evaluated its performance. So the analysis that I have described shows the load balancer works correctly, and the hashing function was the impact that was affecting the load distribution. But now when we improved the hash function, we achieved a more balanced system without changing the overall architecture of the balancer. Thank you.